I'm Doug, Stand-Up Physicist. Today I'm going to discuss 4 potential theories for gravity and light. This is really a topic that I think is an area of blindness in physics. We are familiar with visual blindness, but there are actually many forms of visual blindness. There is color blindness, where you cannot see red or the difference between red or green because you don't have the protein in the back of your retina to do that sort of thing. But there are forms of blindness that are actually associated with how you process information. There are people who cannot tell the differences between faces, even if they've lived with someone for decades. And there is a form of blindness that's known as that deals with 3 dimensions. People can't see 3 dimensions. Everything is on the same plane to them. Now, when you look out at something, your eyes actually see slightly different things. And you have this ability to subtract one from the other and then order things in space. And we're very fortunate that we don't have to do that calculation with a sheet of paper. It's just hardwired in here. For most of us. There was this story on NPR of this woman. I think she was a neuroscientist. And she was reading about this condition. And it sounded kind of familiar. She thought she might have it. So she invited a friend over to give her the test. And she failed. So she read more about this condition, and she found out that if you're an adult and they give you this test and you fail, that's the way it is. So she decided to do an experiment. There are exercises you can do to improve your depth perception. You basically focus on something here, something a little further, something a little further still. Now they looked the same to her, but she was setting up the things so she knew they were at different depths. And she did this for a month. And like the literature said, it didn't really change anything. But she was persistent, and she did it for another month. And nothing happened. Well, by the 3rd month, nothing happened either. And it was like more than 6 months of doing these exercises and getting nowhere that she started to think that maybe she started to see something. And one day she was walking outside and it was snowing. And she just stopped because she could finally see the layers of snow falling. And she was just really struck by how beautiful a snowfall can be when you see it in 3 dimensions. That tells us a few things, that story. That is that sometimes you really have to do a lot of work to see something that should be right there. I hope that a gravity theory that deals with that's 4-dimensional potential is like that. Now we have a 4 potential theory for how light works. And it is the best field theory we have in all of physics. It's known as the Maxwell theory, and it really is great. But there is no gravitational counterpart. Now, a blindness should be a measurable thing. And if you say, I'm going to go and read up all the papers that deal with gravity as a 4 potential theory, well, you won't have to do a lot of reading because I've got the 2 papers, all right here, that go into it, and that's it, all right? And they only spend like 2 paragraphs each, and they just say, you can't make a theory where like charges attract. Well, you certainly have to do that to have a theory for gravity, but there are like 5 different reasons I know of in my proposal why like charges attract. They don't list which one of these is a problem, so I can't really refute it because it's not mentioned. They're like too quick to kick it out the door. There's another way. You can look at modern surveys and see if it's in there at least. And this is the best one out there. This is written by Clifford Will. He is a very smart, very good guy who looks a lot like Ted Turner. And it's over 100 pages. It's got like 150 plus references. This guy knows his stuff, okay? And it's got a section on alternative approaches to gravity, and it's not listed, even as a possibility. So I went to talk to Professor Will, and I said, Clifford. Actually, I probably said Professor Will because he's just smarter than I am, or more knowledgeable about stuff. I said, why didn't you include a potential theory? And he said, well, because you can't make a potential theory where it works to explain how light bends around the sun. We've got Newton's potential theory, which has one little potential in it, and it actually gets the story half correct. Now, the thing with dealing with someone like Professor Will is he's too smart to say he's wrong, okay? The most you can possibly hope for is to say he's right up to here and he doesn't see the thing beyond it. Now, what he sees correctly is that Newton's theory is a potential theory. It's got one thing, and it tells us that the difference in time gets a little smaller because of gravity. And it's right on, okay? But it doesn't also tell us that the distance for space things gets a little larger. Well, because it's only got one number to play with. And if you got one number to play with, you can't make one thing smaller and another thing larger. You're just not enough cards in the deck. But if you had a 4 potential theory, then you could make the time part get a little smaller, like Newton's potential theory does, and you could have another potential that gets the distance a little bit larger, okay? And the other two, they come along for the ride. There's so much symmetry around it. You don't need them, okay? Maybe another more complicated situation, they come into play, but they basically not needed. But if you had that sort of situation, you could explain light bending around the sun rather easily, actually. So I feel like I'm in this situation where I see the snow falling really clearly in 3D. I understand why they don't go through the work. It's not, they don't have to read about it, like it's not written about, and I can see why I can see it and they can't. And believe me, it's very beautiful from where I stand. There are at least 3 problems with 4 potential gravity. First of all, you must show that gravity in fact attracts, a very basic property of gravity. You must end up with a force law that depends on an inverse square distance, as Newton proposed so long ago. And the equations are rank 1, linear, and bind to the rest mass, and quite frankly, all 3 of those are against the dogma of general relativity. And I'm going to actually throw in a 4th one, and that is that you must get the spin of the particle that causes gravity correct. It is a spin 2 particle. So the first problem deals with gravity being an attractive force. The problem is, if gravity is modeled exactly on Maxwell's equations, then like charges repel. And the solution to this problem is one well-chosen minus sign. Here we have the proposed unified field equations. And you can pick out the Maxwell equations in the Lorentz gauge. Then we can look at Gauss's static law, where if you use Gauss's law on a sphere, you can actually show this indicates that like charges repel. Now, if we go and we look at Newton's static law, which is also contained in here, we notice that the signs are the same. Therefore, if we apply Gauss's law to this particular equation, it's going to be darn similar, except for that one twist, which means that like charges attract. And one of the nice features of this is that we can actually make Newton's law relativistic. Now, this was one of the motivations for getting general relativity, and we don't have it anymore because this does transform politely under a Lorentz transformation, specifically as the first part of a four-vector equation. So the second problem has to do with the form of the force law. The problem is that the inverse distance squared potential that solves the 4D wave equation leads to an irrelevant inverse cubed force law. The solution to this problem is to use perturbation theory. The idea is that we start with what we know is a physically relevant solution. That would be m over r. And the m over r potential solution then has a good force law. But that is a static proposal. So what we look at is the least dynamic possible solution, basically by using perturbation theory. So here is the perturbation solution. We use this sigma squared, which equals r squared minus c squared t squared. And we normalize this, and we use a little perturbation by k. And if we only keep k terms to the first order in k, then we can get the correct sort of dependence on r. Now we get into a dogma dogfight. General relativity has several properties to it. The field equations are non-linear. The field equations are rank 2. Gravity binds to energy momentum. Get in a rocket ship and look at that energy momentum, and it becomes a rank 2 tensor in the field equations. The equivalence principle states that the passive gravitational mass plus every sort of energy you can find is exactly equal to the active gravitational mass. In other words, one that's involved in gravity versus the one that's involved in inertia. And that includes the energy of a gravitational field. These four statements sound very different, but they're all telling you the same message. The reason that the equations are nonlinear is because we're putting in the gravity field energy. And it's a rank 2 field equation, and we have this energy momentum binding, which actually ends up looking like a rank 2 tensor. So if you were to go against one of these, you actually had to go against all four. And here is the gem dogma. The field equations are linear. The field equations are rank 1. Gravity binds to rest mass. This one is going to actually cause me the most trouble. Now you get in a rocket ship and you look at this and it becomes an energy momentum 4-vector. What that means is that whatever sort of energy you want or whatever sort of momentum you want, you can put it into this expression. Now, it does respect the equivalence principle, but in an ever so slightly different way. You do get to add in, of course, the passive gravitational mass and every sort of energy or momentum out there you can find, with one exception: that gravity fields do not gravitate. And that is connected to the idea that these equations are linear. So I want to do a thought experiment because it's one that's used to justify that gravity must be non-linear. I think the dilemma here is that gravity binds to the stress energy tensor, or electric charge is conserved, but not both. So this is from Price's review of, or primer to general relativity. And you have two boxes, and they each have 6 particles in them. And if one of the particles in box 2 was converted to the motion of the other 5, then would there be any way of box 1 knowing that anything like that actually happened? And if you say, I don't believe that there's any way that box 1 could know what happened in box 2, it's either 6 particles that are standing still or 5 particles that are moving around with them as all the vim and vigor that was in one of those, then that would mean that it binds to the second rank tensor. Well, I'm going to make one more specification, that each and every particle happens to be an electron with 511 keV of rest mass and -1 unit of electric charge. Now, when you do this, then the thought experiment becomes impossible to do. The reason is that you cannot destroy an electric charge. There are actually experiments that show this to a high degree of precision, and also theoretically, it's just a non-starter. You cannot split the electric charges into fifths and redistribute it. So this whole thought experiment, I believe, is simply not valid. It cannot be done. Finally, there's this issue of spin. For gravity to have like charges that attract, the spin of the mediating particle must be 2. Why is that? Well, first of all, it must be an even spin to be attractive. And second of all, it can't be a spin 0 particle, because if it was a spin 0 particle, it wouldn't be able to get light to bend, and yet we've seen light bending, and therefore it's got to be something greater than spin 1. It's got to be a spin 2. Now, there are actually 2 reasons to be able to see a spin 2 particle in my proposal. The first and easy one, and the one I saw right off the start, was that my field strength tensor is rank 2 and symmetric. And that's just the kind of place where spin 2 particles live. But the second reason was actually more subtle, and it has to do with the coupling of the potential to the current. And if you do the kind of analysis that Feynman was so good at, then you would show that it looks like it should be a spin 1 particle. Well, here again, what we need to do is do a twist at the appropriate place. If you do a twist at just the appropriate place, you can actually show, or I've been able to show, that the resulting current actually has the symmetry of a spin 2 particle. And so I believe that's the one missing thing, or that's an important component to the proposal, is that I can see a spin 2 particle in the current coupling term. So although there are these wonderful objections to the proposal, I hope I have addressed them.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling
going to talk about me and Britney Spears. Now, most people know Britney from her music, but I learned a lot from her from a website, Britney's Guide to Semiconductor Physics. If you haven't been there, let me just give you a small sense of it. Okay. See? It's a real website and deals with some complicated issues, like this is finite barrier quantum wells, which is really important understanding semiconductors. Now the math gets kind of serious here. There's no way around it, you know. If you're a real artist, or an artist, you have to get into this stuff. But you know, you get a reward at the end, you know, and a nice result to look at. So I was so impressed with that I decided to join an official fan club. And I started to talk about band gap issues. And it took a long time because she's a very busy woman. But she eventually got back to me and pointed out that my question was, ooh, it was very wrong. And that's the way it goes in science, actually. As often, it's not that your question is close, it's just like totally off base. And she pointed out to me in a nice way. And so we really started to establish a relationship. I started to call her B for boron, an inert gas. And she was a good Southern girl, and she said, she doesn't have inert gas. She lets out loud ones, if you know what I mean. Because that's the way they are in the South. They learn the high culture and the lowbrow stuff too. Very endearing. She actually invited me backstage to one of her concerts, the one in support of the third album. And it was just amazing. I mean, to go backstage, all these people milling about, all these security people, you know, what was your level of your badge, you know, mattered so much. I was able to actually get close to the stage and could see both she and the whole team kind of working together. And so everyone went backstage after it was done, and we were all kind of relaxing. And I was, you know, relaxing too. And, you know, I just started talking about my stuff with quaternions and four potentials and how it was all being, like, ignored. And that's when Britney said, you know, she felt the same way because for her third album, she was trying to put more of her own songwriting in, and people were just being really rather unkind and ignoring the important work that she was doing. And so we really connected on that kind of level of being artists and trying to be true to the art and nobody caring. She said, you know, that BS guy, which I later figured out was Bruce Springsteen. It's like apparently she doesn't like Bruce. Said that BS guy can put together an album like Nebraska, which you should be able to just like hand to a judge and say, this guy should be put in a mental institution where they've got state troopers on every single floor, okay? And people say, oh, he's great. Well, I actually kind of like the Nebraska album, so I was like, yeah, I guess you're right about that. And so she finally, she took my hands, both of them, clasped them together, and she said, you know, the one thing you have to remember, Doug, is that this entire thing here, with you being with me backstage at the Garden, you're making it all up. None of this is real. So you have to be true to your art, even if everyone ignores it. And I thought that was like really true, but I wasn't sure whether I should thank her, because if she wasn't real, then she was a projection I was making up and then coming back to me. And so it'd be kind of like me thanking myself for some insight that I guess I already had. I was confused. I mean, what are the social rules about thanking yourself? But I got the photo, which I printed off the printer back here, and I signed it myself. It says Quaternions rock, and so this is real, and I'm going to keep it. I'm going to keep going on with the physics and the Quaternion stuff, and maybe someday other people will see that it is real too.
Rock star.